In this webinar, we're going to talk about some durability fundamentals, specifically pertaining to fatigue analysis. So Miner's rule, SN curves, and rain flow counting are all tools that we use to analyze fatigue data. So to get started here, we're going to jump into just some basics before we start talking about any of those topics further. I want to just cover what is stress, what is strain, and then finally, what is fatigue and what's the difference between a static stress-related failure and a fatigue-related failure. We'll just jump into these basics. We've got a little cylinder here. It has a cross-sectional area along the top here denoted AO. There's a applied force here in compression, and we would define the stress experienced by this cylinder as the applied force divided by the surface area of the cylinder. Stress is typically expressed in units of pressure, force over an area. We normally denote it in things like megapascals or for English units in PSI. And stress is one of the, I'll call it, typical quantities that we are trying to monitor when we're talking about a durability analysis. Stress is kind of the quantity that we relate directly to the applied load that might cause the failure of a test specimen. From the analyst's perspective, we may want to know how to reduce the stress in a part to either improve the fatigue life or to make sure we don't exceed the static strength of the material with any loading. To reduce the stress experience, we can either increase the cross-sectional area on the part or reduce the applied force. Now, if we were to reduce the cross-sectional area here, so we're cutting some little notches in this cylinder, this area would cause a stress concentration. Notice that the effective cross-sectional area has decreased, which would mean an increase in the stress on the specimen. So especially from a design engineer point of view, it's important to be really careful around cutouts in a material, bolt holes, welds, and sharp corners, because these reduce the effective cross-sectional area of the object and can lead to higher than expected stresses. The other quantity that we'll be very interested in is strain. So strain is the change in length of a test specimen over the original length when a load is applied to that specimen. So I've got the same cylinder here. It has a original length, L0, and then I apply a load, and the change in length due to that applied load is shown here. So this delta L is equal to the instantaneous length divided by the original length. I take that change in length, I divide it by the original length, and I get the strain on the test object. Note that this quantity strain is a length over a length, so it is unitless. Any quantity of length like meters over meters that we get here, they cancel each other out. We often express strain in a unit, just to make things more confusing, which we call microstrain. So this is not a real unit. Always remember that strain is unitless, but we often attach the word microstrain to a strain quantity, and we take our actual strain value and multiply that by 10 to the -6, because strain quantities, this change in length over length, is usually extremely small, especially for metallic materials. This delta L can get much larger for rubbers or some thermoplastics, but for metallic materials, this delta L is very small, so it makes sense for us to multiply the strain value by 10 to the -6 and give it a kind of an imaginary unit called microstrain. We can relate stress and strains. Typically, if we're doing especially an FEA analysis or a fatigue analysis, we want to use stress as kind of our metric to determine how long something might last in the field before failure. Stress is hard to measure directly. Strain is much easier. So oftentimes we measure strain and then we convert that to stress using something called Hooke's law. Now, Hooke's law describes the relationship between stress and strain. We can express it. In this case, we're showing it in this formulation where we have the modulus of elasticity equals the stress divided by the strain, or we can write this as the stress is equal to E times the strain. And this parameter E describes the slope of our stress strain curve. So if we were to put a test specimen in a testing machine, we apply some loading to that test specimen, we monitor the stress and we monitor the strain at the same time. For a while, that metallic material will have a straight line or a linear slope, and that slope E is called the modulus of elasticity. It's typically expressed in MPa or GPa, gigapascals. So this is normally a relatively high number. We call this the elastic region of the material or the linear region of the material. In this region, if I were to apply a load to a material specimen, let's say up to here, and then remove that load, the material would return to its original shape. So there would be no what we would call plastic strain in the material, or no offset strain from that applied loading. It just returns back to its original shape, no permanent deformation. Beyond this elastic point here, the onset of the plastic region is denoted by the yield strength of my material. If I exceed that plastic region, let's say I go up to this point here, when I remove the load from my material specimen, I do not go back to the original shape of my material. There's some permanent deformation due to the applied loading in this plastic region. We're past our yield strength here. We have a point denoted as the ultimate strength of the material. So this is the maximum stress or maximum load that the material can experience before the stress starts lowering here, the strain starts increasing rapidly, and we eventually get to this fracture point where the material fails. So let's talk a little bit about fatigue and the difference between dynamic loading and static loading. So the static strength of a material is the load which causes failure in one application. If I had a little metallic bar, let's say I'm an exceptionally strong man here and I bend that bar, bend it in two basically and cause a fracture in the middle of the bar, the load that bar could undergo before failing is essentially the static strength of that little piece of bar material. So anything that would cause failure in one application. Fatigue refers to the gradual degradation and eventual failure that occurs under loads which vary with time. So in this case, we're essentially in the static strength case, we're just applying kind of a single point load. For fatigue, we're applying a dynamic loader, one that varies with time. And the load which causes failure is lower than the static strength of the metallic specimen. In this case, without perhaps a trained eye, we might say, oh, our loading on our part is below the static strength of the material. That means that we won't experience failure on the part. But due to metal fatigue and the mechanisms of metal fatigue, our parts or our devices, our products, can fail when they experience a load history that is well below the static strength of the material. And we'll talk about why that is here further along in this presentation. But primarily what we'll be talking about is this fatigue failure aspect of durability testing and analysis. The mechanism for fatigue is the onset and propagation of tiny cracks in the metallic specimen. And so we've got an image here of a crack forming in a material, a nice blown up image of that same bar here where we can see that there's a point where a crack initiates, and this is typically caused by irregularities or imperfections in the material that's being used. So there might be, due to the manufacturing process of the material, some local stress concentrations already. And then when we apply a loading to the material, this crack starts to propagate, so it gets bigger and bigger. You can see this crack propagating through the material, and then eventually, once the crack reaches a certain size, it starts to propagate unstably through the material and causes fracture. So in this next slide here, we have a nice video showing a controlled test where there's an instability in a material that's been provided on purpose, and we'll watch that propagate as load is applied to this object. So you can see that crack propagate on this metallic specimen. Here's an example of what we would consider a static strength test. So this is a bending test on an airplane wing. Basically, a load is applied on one end, and we're going to bend this airplane wing until it breaks. It's really kind of quite amazing how flexible these airplane wings are. I'm actually going to even skip ahead in the video here a little bit so we can get to the failure point a little faster. But this would be an example of a static strength test, or you may hear the word quasi-static get thrown around, where this is changing slightly with time, but not quickly enough to where we can't use kind of a static approximation to discuss it. So here, after a certain amount of time, you see that airplane wing finally fail. And this is a static failure. We went past kind of the ultimate strength of this airplane wing. A fatigue failure would be something more like this wind turbine. It's operating in a very windy and gusty environment, in a very dynamic environment. And so this turbine blade is turning, and eventually a crack forms. That crack causes, that crack propagates through the wind turbine and eventually causes one of the blades to break off in a catastrophic failure. Let's see if I can maybe get that to replay one more time. So a crack forms, it propagates through the wind turbine, and then eventually causes the failure of the entire wind turbine. So an example of a fatigue failure versus a static failure. We'll go into a little more background just on the history of fatigue. Fatigue failures weren't really analyzed or considered until an enormous railway accident in France in 1842. There was a massive train derailment caused by a broken axle on the train that killed over 200 people. And as a result of this accident, several different prominent engineers and mathematicians set out to determine what the root cause of the failure was. And what they initially found was that the axle was designed properly. The loading on the axle was not exceeding the static strength of the material. But what this guy, Wohler, discovered was that as this axle was rotating, parts of the axle would see a positive stress. So at this location here, there'd be a tensile load perhaps. And then as the axle rotated, a different part of the bar would start seeing a compressive stress. So he noted that there were these fully reversible cyclical loadings that the axle was undergoing each time it made kind of one full revolution. And he hypothesized that this cyclic loading was what was causing the axle to fail, even though the tensile strength, or the ultimate tensile strength, was higher than the max cyclical stress range. And he termed this as fatigue. The origin of the name is actually, I'd say, kind of cute. They were saying, oh, the metal is getting tired. It's fatiguing, and that is what is leading to the failure. So there's three general parameters that influence the fatigue life of a part or of a component. The first one is the loads experienced by the part. So the obvious ones here are the load level. If you apply a very large load, that has a larger effect on the fatigue life than just applying very small loads, and the mean stress of the loading environment. And so loads in tension typically cause the crack to open up more, while as loads in compression, so that have a mean compressive stress, tend to close that crack. They don't cause as much fatigue damage as loads in tension. There's an effect of whether the load is constant amplitude. So is it a single essentially amplitude stress cycle? So for example, a load which goes from 100 newtons to minus 100 newtons back to 100 newtons and just keeps repeating that way? Or is it a variable amplitude load? Is it something that looks more like this time history here, where the load is fluctuating in level with time instead of being a constant value? And then things like, is it a uniaxial stress state or a multi-axial stress state? The geometry also has a large impact on the fatigue life of a component, especially given things like the notch severity. How many cutouts does my geometry have? How many sharp corners does it have? How many essentially locations where I can introduce a stress concentration into my component? And this is something that CAE analysts need to be careful about, and something that they need to design for is essentially trying to reduce the notches and reduce the locations where stress concentrations might occur in a part or a component. So I'd say in geometry, this is very much so something that the CAE engineer controls during the analysis portion of a fatigue analysis. And then finally, the material properties. The basic properties of the material, like the ultimate tensile strength and Young's modulus, the yielding point of the material, and then things like what's the surface finish on the material, or how was it manufactured? Things that are polished, for example, don't have as many stress concentrations as something that has a more rough finish, and so a polished material would have a better fatigue life than something that is left unpolished. A material can also have residual stresses due to the manufacturing process. So if it has a residual tensile stress, that part will fail more quickly than one without that tensile stress, and so on. When we're designing a product, or when we're analyzing the fatigue behavior of that product, we really have three questions that we need to ask ourselves. One is, what is the loading environment of our product? So do we know how the customer is planning on using that product? That will allow us to kind of define the loading envelope that we expect. We need to understand the geometry. Where are the locations where there will be a stress concentration, and how severe is that stress concentration? And we also need to know the fatigue properties of the material that we're using. So we'll discuss this first aspect here, loads, and how we kind of determine those loads and some of the methods that we use to analyze a load time history. I've got a slide here. This green curve right here, kind of ending right here, is defining the probability density of the loads that I might apply to my product. And this curve here is defining the structural strength of the materials that I'm using to make that product. There's more scatter on the potential loading environment of my product because we can't control how a customer might use our product. We can to a certain extent, but there's always going to be people who push the limits or push the boundaries of a product and maybe use it in a way that was not considered or intended by the designer. And so loads typically have more scatter, they're less predictable because of our customers, whereas the materials have much less scatter. We more or less kind of understand the material properties associated with a particular design. Our goal here is to minimize the overlap of our applied loads and the structural strength of our material. So we say here at this location here, at the extreme end of our applied loading, so maybe this is a larger, statistically maybe less probable load here that we would apply, and at the other tail end here, maybe we're at the statistical end of our material where due to some manufacturing irregularities, it's weaker than it would be at other points in this curve. We see this failure point, and our goal is to make this as small as possible while also making sure that our product doesn't have any unnecessary material that's maybe adding weight that might affect the fuel economy of a car or an airplane, or just increase the cost of the production of that material. So in the optimal design, there's minimal overlap between these two items. But again, it's a big challenge to determine exactly what this curve looks like because we can't control our customer usage. Over design would see something like this, where we've really over designed our product. So there's a wide gap between the worst case loading scenario and the worst case material strength scenario. And this might be the design approach you take for a product that cannot fail. So maybe in the aerospace industry, there's a component for which failure is not an option because it poses a safety issue. You might employ a design philosophy like this one. And then finally, a not so great design would be where the loads and the material strength overlap significantly. This means we would have a high probability of failure. So here are some things we might want to take into consideration when we're either designing a structure or a product or a component. We want to understand how that product is going to be used. So in the example of this loader here, gathering the soil, digging and loading, the bucket travel, dumping, and leveling operations will all have different loads, I guess, applied to this vehicle. So it's important to understand that from an analysis side of things, and also important when we're performing testing to try and capture the correct load time histories during all of these different movements or operations for the vehicle. And each of these different pieces of equipment might have all of these different types of loads applied that for analysis we need to capture correctly. We might also have extreme modes of operation, and it's important to, as the designer, consider whether or not we want to design for these extreme operating conditions. So is this something that we need to consider when designing this piece of machinery? So we're going to talk now about how we actually go about calculating fatigue damage, and it's going to include considerations on, the load time history, the material properties of whatever we're using to whatever we're building this component out of the material, and local stress concentrations, which may be caused by the geometry of our material. So the first thing we're going to highlight here is how do we get useful information out of a load time history. So it might be something like a force versus time curve, a stress versus time curve, or a strain versus time curve. And to illustrate a challenge we have when analyzing loads is we can look at measurement A and measurement B. These measurements have the same number of cycles, but the amplitude of the cycles is larger in measurement A than it is in measurement B. So if we were to compare these two measurements and we had to make a decision, which one of these will cause more fatigue damage or is likely to cause more fatigue damage, it's relatively easy. We can qualitatively compare the amplitudes here, and we can say, aha, this one has a higher amplitude. Measurement A is likely to cause more fatigue damage than measurement B. However, in the real world, we usually don't have nice sine waves that we can compare. We have something more like this, where we have a variable amplitude loading environment. So our load is, kind of dynamically increasing, decreasing. There's maybe a dynamic component and a mean stress component. And if we were to look at these two load profiles, in this case, between maybe driving over road A and driving over road B, it's much more difficult for us to say which one will cause more fatigue damage. And so we need a tool that we can use to analyze this time history and kind of spit out a number at us, kind of tells us which one has more fatigue damage potential. And we'll use damage calculations. We'll use something called Miner's rule to calculate how much damage a particular loading curve contains. Before we apply Miner's rule, and we'll discuss that again a little later in this presentation, we need to break down these complicated load histories, so road A and road B, into something that's a little easier to understand and or analyze. And the way we do that is by doing something called a rain flow count. Rain flow counting is a histogram method where we analyze a time series and we break it down into its basic load cycles. Rain flow counting was thought up by a Japanese visiting professor at the University of Illinois named Tetsuo Endo. And it is a technique to decompose a spectrum of varying complex stress into a set of simple stress reversals. And so it allows us to take something like this load history and decompose it into a certain number of cycles at different amplitudes. So I can say this curve here consists of maybe 4 or 5 cycles at a set amplitude, and then 4 or 5 cycles at a slightly lower amplitude, maybe 3 cycles at a lower amplitude, and so on. And I like to kind of compare rain flow counting to the Fourier transform in the way that in a Fourier transform, if we were to take an FFT on a set of time data, we break that signal down into its constitutive frequency components that are the building block of a signal. Rain flow counting does something similar, where we are instead breaking this signal down into its kind of constitutive stress, strain, or I'll call them load cycles. So let's talk a little bit about how rain flow counting works. So the input is a load time history, and we perform a number of pre-processing steps to remove kind of unneeded or unnecessary data in our signal. So we do some hysteresis filtering. The purpose of that is to remove any cycles that do not cause damage. So anything that is small enough to not cause damage gets removed. We then remove the data points which are not reversals. So for example, this point in the middle here is not a reversal. It just lies on this kind of straight line here. So we can remove that point here and only keep the points which are reversals on the time signal. And then we put these different points into a number of bins. And so we'll go into each of these steps in a little more detail here. So the first step in a rain flow counting method is to filter the data using a hysteresis filter. We designate a filter size, and then what we do essentially is say, anything that is below this filter size, remove from my time signal, because I know that any stress, strain, or load cycles below this filter size will not cause any damage in my part. So I sweep my filter across my time series here, and you can see that there are certain reversals here, like this one right here that I'll highlight, that get filtered out by my hysteresis filter. We then take kind of our more complicated signal with many different samples, and we throw out any of the samples which do not contain reversals. So we might go from something like this to a more linear curve that looks like this, that only contains these reversals, because these reversals are what will cause damage on our product. We then put the leftover samples into a number of bins. So the rain flow counting method in test lab, we can specify a certain number of bins, and we map the sampling points to the center of the respective bin. And consecutive points lying in the same bin are removed. For example, here we have this point up here, which is not lying at the center point of a bin, so it gives moved up slightly to the center of this 5-point bin. We have 2 points here that are consecutive points that are in the same bin, so this point gets removed. It's important when you're doing a rain flow analysis to make sure that you have enough bins in order to not change the amplitude of these points by too much, and some kind of common numbers that are used. I believe the standards describing this rain flow counting specify usually at least 64 bins. More commonly, I see people use over 100 bins when doing this type of analysis. And so now after these pre-processing steps, we can get to the fun part, which is the actual rain flow counting. What we are looking for in our time history is closed loops. And these closed loops represent fully reversible cyclic loads. And so if I look at this time history here, I can see that I have a closed loop right here where I go from this point we've denoted 8 down to 0.7 and back up to 0.8. I can take that cycle and I can plot it in what is essentially a histogram, where I've got from on the y-axis here and the to load level on the, we'll call the x-axis. So I go from 8 to 7 back to 8. So I would put one cycle in my from 8 to 7 cell in my rain flow diagram. I could then continue going through this time history looking for these reversals. I've got another one here from 4 to 3 back to 4. I could plot that in my table. And then continuing on, I see I have a point here from 2 up to 5, back down to 2. And I would plot that in my rainflow matrix. And I would go through my entire time history looking for these load cycles. And after one is counted, it's removed from the time history. So I remove any of the previously counted load cycles and continue looking until I've basically counted every single load cycle in the time history. And this here is our rainflow matrix. We'll use this rainflow matrix when we're calculating the fatigue life. So the rainflow matrix describes the load history that our component, our part, is undergoing. And now we'll use that in conjunction with some material properties, namely an SN curve, to calculate the amount of fatigue damage that our part might experience. We'll start off our discussion on SN curves with a little experiment that you folks at home could play around with if you had a desire, where we take a paper clip and we bend that paper clip back at 4th at a certain angular increment, and we observe how many times or how many bends we can make before this paper clip fails. So starting with a plus or minus 10 degrees repetition, and then we'll do plus or minus 20 degrees, plus or minus 45 degrees, and plus or minus 90 degrees. We can see that at an angle of 10 degrees, it takes 79 cycles for the paper clip to fail or break. At 20 degrees, it takes 29 cycles. At 45, it takes 7. And at 90, it takes 1.5 cycles, or just 1.5 cycles. We can plot this information, the angle versus the cycles to failure, where on the x-axis I have the cycles to failure, on the y-axis I have the angle, and I get a SN curve, or a Wöhler curve. This describes essentially the load level that my part can operate at until failure. So for a very high load level, I can only undergo a few cycles before failure. And as I decrease that load level, my paperclip can survive many more cycles before failure. And so typically we look at this on a log-log scale. For real components that are not paper clips, Wöhler was one of the first guys to perform this type of cycling test on railway axles. So he would apply a cyclic load with a constant amplitude, and he would record how many cycles that axle could go through before failure. He would then take another railway axle, he would apply a higher or a lower load level and cycle that until failure, and so on. And so by cycling these railway axles at these different load levels, he was basically able to build up a component SN curve for these axles. Typically what is done today in the lab is we will take a coupon of the material. So in this case, we're showing a little piece of structural steel that's got a notch cut into it to allow us to kind of control the area where this coupon will fail. We'll put it in a coupon testing machine, and that coupon testing machine will cycle this component at a constant amplitude cyclic load until we get fracture. And then we record the number of cycles that it was able to withstand before failure on our plot here. We then take another coupon and do the same test, but this time we vary the load level. And if we get enough data points, we can build up an SN curve for that material coupon. So another way of looking at it, this where we've got all of these different data points in black here, and then we basically take a linear regression between all of the points and we get the SN curve for the coupon and the material that that coupon was made from. Let's talk a little bit about an SN curve and kind of what these different regions of the SN curve are. So we have stress amplitude on the y-axis and the number of cycles to failure on the x-axis here. And what this SN curve tells me is at a particular stress level, how many cycles at that stress level could my part undergo before it fails or fractures. I have the ultimate tensile strength of my component here. That's the point where after one cycle, this load level will cause failure. And then I have this point down here on my SN curve where for some metallic materials, I exhibit something called infinite life, where any stress level below this region here will not cause failure of the part. And then this point here on my SN curve is denoted by the yield strength of the material. I have several different regions on this SN curve. I have the infinite life region. I have the finite life region. And then I have the high cycle fatigue region where my loading is purely elastic. So I receive, or my part sees no plastic deformation as it's undergoing these cycles. And then the low cycle fatigue region where my part experiences plastic behavior, the load levels are much higher, and I can undergo fewer number of stress cycles before my part fails. It's important to note that SN curves are made by testing material coupons and not an actual component that we wish to analyze for its fatigue strength. If we want to use an SN curve for a fatigue analysis, we oftentimes need to make adjustments to the baseline SN curve to account for differences between the coupon that was tested and the component that we are analyzing, as well as for things like the loading. So in the real world, our load histories are usually variable amplitude loading instead of the constant amplitude loading that we use when generating an SN curve. And in addition, we usually do cycles in tension and compression instead of things like moments, for example, applied to the coupon. We also might need to apply adjustments for the size of the coupon, the surface finish of the coupon relative to our actual part, and adjustments for reliability. Maybe we want to apply kind of a safety factor on our SN curve to account for the fact that generation of these SN curves is essentially a statistical process where we're failing a certain number of coupons of samples, and then we're using those as our data points for the SN curve. And the more samples you test at each load level, the more accurate your SN curve. So here's just an example of some adjustments that can be made to an SN curve to account for the different loading types that might be applied to the actual device under test that we want to analyze. It's important to highlight that fatigue is logarithmic in nature. I've got a little plot here that on a log-log scale shows the number of cycles to failure on this x-axis, the load level on the y-axis. And I can see that if I reduce my load by 13%, so if I go from 100% load to 87% load, I get an increase in fatigue life of 2 times. Changing the load, either by reducing the load level or increasing the load level, can have an enormous impact on the fatigue life of a part. So it's not as simple as saying if I reduce my load by half, my fatigue life goes up by half, or if I increase my load by 50%, then my fatigue life goes down by 50%. Because of this logarithmic nature of fatigue, we need to be very careful when we're performing an analysis and changing our load levels. The material also has a large influence on the fatigue life. So the slope of the SN curve, or the run of the SN curve, is called the Basquin coefficient, or the K factor, and it determines how, essentially long my slope is, how much run the slope of my SN curve has versus the rise. And if I increase the load level on a component, so let's say I go from 100% load to 130% load, I can see that my K value, or the material value that I'm using, can have an enormous impact on the fatigue life of my part. So if I go from a K equals 3 to a K equals 7, I get a reduction in my fatigue life by a factor of 3. This logarithmic relationship is really important to keep in mind, both from understanding the loads that our material where our specimen goes through and the material properties of that specimen. Okay, so now we'll get to the final part here, which is how we take the information we get from our rain flow counting, so our histogramming of our load time history, and the material properties from our SN curve, and how we use that to predict the fatigue life or the amount of damage that our part accumulates under that particular loading. To understand the fatigue content of loads and to come up with this damage value, we use something called Palmgren minor damage accumulation rule. This is a linear damage accumulation model, which basically states that if I have 500 cycles of load type 1, designated in red here, 1,000 cycles of load type 2, designated in green here, and 10,000 cycles of load type 3, designated in blue, I can accumulate damage by summing the number of cycles I have at a particular interval and divide that by the number of cycles to failure on my SN curve at that particular load level. And when I get to a damage value of 1, I say that is when my component has failed. And so we can illustrate that here. If I look at my SN curve at load level 1, I can undergo 1,000 cycles before failure. At load level 2, I can undergo 100,000 cycles before failure. And then at load level 4, I'm in the infinite life region. So I can run it at this particular load level indefinitely. I use my minors rule. I take 500 over that value here. I get 0.5. I take my value here. I have 10 to the third power, so 1,000 cycles here. I divide that by 10 to the fifth. I get a value of 0.01, and I say my damage value is the sum of these two here. So I get 0.51 damage. We'll go through another example here where I've got a time signal, an SN curve, and we'll cycle count this to determine how much damage has been accumulated. I've got 2 cycles of a particular load here, and the cycles to failure is 6. So to calculate the amount of damage that my component will accumulate based on this load cycle here, I simply take the number of cycles 2 divided by the number of cycles to failure. At this point on my SN curve, we're saying that's 6, and I get a damage value of 0.33. If I add in some more cycles at a higher amplitude, I add in 2 more cycles, I can do the same thing where I now have 2 points on my SN curve that I need to make a comparison to. Let's just look at the orange curve here. I can say that I have 2 cycles of the orange time history, and it takes 4 of those cycles before my component fails. So I have a damage value of 0.5 due to the orange time history, and to get the total damage caused by this entire time history, I just sum those 2 values up and I get a damage value of 0.83. So I don't see failure in this case. If I add another cycle of my orange time history, I now have, due to that orange component, 3 cycles divided by my 4 cycles to failure, so I get a damage value of 0.75, and my total accumulated damage would be 1.08, which means according to Miner's rule, part has failed. I've accumulated enough damage that a fatigue failure has occurred. This Miner's rule utilizes, again, both our rain flow counting methodology in order to calculate the number of load cycles at different amplitudes, and then just directly compares it to the material SN curve to accumulate damage according to Miner's rule. We can also do some things when doing a fatigue analysis, like take into account the mean value from the load history. So in this case, the mean value is 0, but there's some corrections that can be made for whether or not this stress time history maybe had a tensile mean value or a compressive mean value. And so now quickly, I'd like to just show you a few of these things in TestLab. I have TestLab Neo open here on my PC. I'll go over to the Processing tab, and I've got some data. Replace that data in my input basket, and maybe just give you a brief overview of the different data traces. So I have some GPS data, I have some accelerometers, some string pots, some strain gauges, and then some GPS information from some measurements that were taken on a vehicle. And I might want to take my strain gauge channels and start off by doing some rainflow counting. So I have a process here that I've created in TestLab Neo where I'm going to allow my strain gauge channels through, and then I'll rainflow count those strain gauge channels. And then additionally, I'll do a fatigue life calculation based on the information from this rainflow method to calculate some damage values. So to start off, I will just run this process and we can look at the rainflow diagrams. I'll go to my active analysis section. That shows me my data that has been processed. It hasn't yet been saved onto my PC's disk. To accept it, I can select this accept button in the corner here. But let's go ahead and look at the rainflow diagram from one of these strain gauges. So I'll maximize this. I can see I have my from and my to axes on this rainflow diagram, and the number of cycles that were counted is represented by the color of the rainflow matrix. There's a few items that I'd like to point out on this rainflow matrix. So one of them is that everything along kind of this center diagonal of my rainflow matrix has a very low cyclic amplitude. So if I stick my cursor here, I can see that the points here on my rainflow matrix are going from negative 8.97 to negative 8.97. So these cycles are not very damaging. They won't cause very much fatigue damage. The cycles at the extremes of my rainflow diagram, so this one is going from 5.40 microstrain to, let's say, maybe negative, we'll just call it negative 8.97 microstrain to make it a little easier to read. These are the cycles that have the highest amplitude and will cause the greatest amount of damage. So if you're looking at a rainflow matrix and you see a very high cycle count of these cycles kind of at the bottom left corner and the top right corner of the rainflow matrix, you'll know that you're accumulating a lot of damaging cycles for whatever action your product is taking at that particular time. Another popular way to view a rainflow matrix, right now we're viewing it in from to, is also to look at it as a symmetric rainflow matrix. So we basically just fold the rainflow matrix in half, or to view it as range mean. Basically now, instead of from to on my y-axis here, I have the range of my load cycle and then the mean stress value of that particular load cycle. In my stress life method here, we're doing the actual cycle counting, so we're comparing these load cycles to an SN curve, and as an output, I get some fatigue life statistics. So I can see the accumulated damage according to Miner's rule. In this case, the accumulated damage is 12.27 e to the minus 6. So not very much damage was accumulated during this particular test. And I can also see the number of times that I can repeat my input load history before failure, before that part fails. So in this case, I could repeat my input time history 81,000 times before failure would occur. Instead of viewing the data in this form, oftentimes people will like to take this and say, well, tell me how many hours my part can withstand based on the input time history, and I can calculate that as well. I can calculate the life and duration, or I could even calculate things like the life in kilometers or damage per hour and so on. So we can play around with these life statistics a little bit to get it into the format that will be most useful for your fatigue analysis. One thing I should maybe also show, or I meant to show, is on the RainFlow method, we can choose how wide our bins are, how wide our hysteresis filter is. We can choose a certain number of bins. By default in TestLab, we choose 128 and go higher or lower and so on. And this affects the RainFlow counting. So both the size of that hysteresis filter and how many of the amplitudes are changed, I guess, or slightly moved to fit the center of a bin on a RainFlow matrix. This is all I had to show today, so I appreciate everyone who attended. I've got my contact information in this presentation, so if anyone would like to have a further discussion about RainFlow counting, about SN curves or Miner's rule, I'd be happy to go into further detail on any of those topics.